Now become familiar with the law of conservation of momentum. There's a quantity of motion called the momentum. It's the mass multiplied by the velocity of an object, and so therefore a vector quantity. The law of conservation of momentum states that the total initial momentum of a system, presumably of two objects, A and B, which I can calculate by adding the momentum of A and the momentum of B, that total initial momentum is equal to the final total momentum, which would be the final momentum of A plus the final momentum of B. Now, the individual momenta of A and B might change. The law of conservation of momentum tells us that the total momentum does not change. If I go about solving problems, I write this in a practical way. MAVA plus MBVB, the total initial momentum, is equal to MAVA prime plus MBVB prime, the total final momentum. When I use this equation to solve problems, I have to be careful because momentum is a vector. And while I've written addition signs here, at any time I could find myself subtracting because I'm adding a quantity of negative momentum. There's a kind of what's sometimes referred to as an executive toy that you may be familiar with called a Newton's Cradle, and it's a very good demonstration of the law of conservation of momentum in collisions. A Newton's Cradle is typically constructed from a frame and 5 steel spheres that are strung from the frame so that they hang like pendulums and they can swing back and forth. All 5 of the masses can swing from the support. But what you do, and the interesting thing, is you grab hold of one of the spheres, pick a sphere on the end, say the sphere on the right, and you pull it back a bit and release it. A rather remarkable thing happens. When the collision takes place, instead of all of the spheres swinging, just one sphere on the far side comes off, swings back, and knocks the initial sphere off again, and the thing clickety-clacks back and forth. If you pull back 2 spheres, you get 2 spheres off the far end. Not surprisingly, if you start the thing pulling back 3 spheres and release it, you might expect what's going to happen. 3 spheres will come off the far side. The reason why this is happening is the law of conservation of momentum. The initial momentum, 1, 2, or 3, has to be equal to the final momentum, 1, 2, or 3, when the objects collide. Here, there's momentum to the left and momentum to the right. The momentum in this situation is always 0, when they're either both going in opposite directions toward the 3 in the middle or in opposite directions away from the 3 in the middle. At every instant in time, one has positive momentum and the other one has an equal amount of negative momentum. The same goes for here, where there are 2 objects involved. At any instant in time, the total momentum of the system is 0, and the momentum of the system remains 0. If you want to be a little bit more clever with the thing, you can try all kinds of different arrangements, like 3 and 2. When you do 3 and 2, notice there's always 3 moving to the right or the left, and always 2 moving to the left or to the right. The total momentum of the system is always the same, no matter what. I was once demonstrating Newton's Cradle live in front of a classroom full of students, and a student asked a really important, and as it happens, classic question. Why not one ball twice as fast? See, what she had realized by looking at Newton's Cradle is that if you release one marble and it comes in and one marble comes off the far side, the law of conservation of momentum is satisfied because one marble goes off comes in from the right and one marble goes off to the left. I don't know how much momentum that is. Let's say it's a momenton. If I have one momenton coming in and one momenton going out, the law of conservation of momentum is satisfied. But imagine instead that I take 2 marbles, pull them back, and release them. When I release them, 2 marbles come off the far side. She was wondering, it had occurred to her, that if I have 2 marbles coming in from the right, like 2 momentons, sure, if I have 2 come off the far side, that's conservation of momentum. It makes sense. But if I have one marble going twice as fast, that's also two quantities of momentum. Because momentum is mass times velocity, so it doesn't matter if I double the mass or double the velocity. So it should be possible that I would draw two masses back from the right, and one mass would come off on the left going twice as fast. The law of conservation of momentum would be satisfied. The thing is, no matter how long you play with this Newton's cradle apparatus, that never happens. Not ever. So I wonder, scientifically, what could be going on there. It's perfectly valid for the conservation of momentum, so why doesn't it happen? And I immediately remember a thing that was said by Richard Feynman, famous physicist. He said that in our universe, that which is not expressly forbidden is mandatory. That means if there's no law that says that a thing can't happen, it must happen. So the law of conservation of momentum is perfectly happy with one ball really fast, and yet it doesn't happen. What that means is that there must be some other law at work, some extra bit of information that we're lacking that prevents one ball coming off twice as fast. And in fact, that law is a very, very familiar one. It's the law of conservation of energy, or in this case specifically, the conservation of kinetic energy. In the context of momentum, it doesn't matter whether I double the mass or double the speed. The effect is the same, double the momentum. So if I have two masses moving at one speed, and then one mass moving at twice the speed, that is equivalent. But if I imagine that in the Newton's cradle process of the spheres colliding one with the other, that energy is conserved, if I double the mass, then I would be doubling the kinetic energy, according to 1/2 mv squared. But if I double the speed, it's not the same. Because the kinetic energy has the speed squared in it, if I double the speed, I get 4 times the kinetic energy. So if I had a Newton's cradle apparatus where two spheres came in and one sphere came out twice as fast, that doubling of speed would be a quadrupling of the kinetic energy. But of course, that still would be half the mass. Nevertheless, it's twice the kinetic energy coming out. That would imply a physical process where not only was the energy not conserved, but the energy magically increased. The reason why Newton's cradle behaves the way it does is it's obeying two laws simultaneously: the law of conservation of momentum and the conservation of energy. You would be right at this point if you were a little bit suspicious about my claim about conservation of energy. When these spheres collide together in Newton's cradle, the energy is not explicitly conserved. The reason why I know this is that, first of all, I can't hear because the sound is off, but you can imagine this thing clickety-clacketing away. It creates a tremendous amount of noise in the form of sound waves that carry energy away from the system. So because of the sound that it makes, the system is losing energy. Also, there's viscous drag involved. As the balls swing to and fro, they stir the air in the room, which also carries around energy. It might be a little more difficult for you to imagine, but as the spheres collide one with the other, their temperature actually increases. The collision, like the friction of your hands rubbing together, increases the thermal energy of the system. So the energy is not conserved here. It is, however, nearly conserved. In fact, it's so nearly conserved that a doubling of the velocity, and which would quadruple the kinetic energy, then divided by half, giving me an increase in energy. The energy lost by the Newton's cradle is far, far, far smaller than that amount of energy. So even though the energy of the Newton's cradle is not explicitly conserved, it's nearly conserved. Reason has everything to do with the fact that the spheres are made of steel. If you had constructed the Newton's cradle out of something else, I don't know, cotton balls, it wouldn't work at all. The reason why is when the steel balls collide with each other, the energy is very nearly conserved. For this reason, we refer to the steel ball and their collisions as elastic. Elastic as the name implies, is like a spring. It involves the conservation of energy. There are two terms that we need to be familiar with here. The term elastic means that the change in energy is equal to zero. That means that the energy is conserved. The term inelastic means that the change in energy is not equal to zero. Energy is lost in some way. The curious thing about this is there was the collision between the steel spheres, and I made an argument based on the idea that the collision was elastic, but I said very clearly that when the steel spheres collide the one with the other, they lose energy. And so I said that the collision was only nearly elastic. It wasn't perfectly elastic. That is, there's always some little bit of lost energy. In fact, there is no such thing as a perfectly elastic collision. You say, no, hang on a second, you're using steel spheres. What I'm going to do is I'll use protons. I'll have two charged particles and I'll shoot them one at the other and they'll repel each other electrodynamically, but they'll never touch. And so they go off and they do their thing and they collide, and then the momentum is conserved and the energy would be absolutely conserved. Actually, it turns out the energy is not conserved, because the thing that you didn't know is that when charged particles accelerate, they emit electromagnetic radiation. And so waves of light travel off into space, carrying away energy. I put a lot of thought into it, and I can't think of a single instance where an interaction is actually perfectly elastic. And yet, very often, I can use the idea of elasticity as an advantage in solving problems. And you might say, well, Shidley, I'm just an innocent, naive physics student. How do I know when it's okay for me to say that a collision is elastic? Well, the answer to that is you don't. In your homework problems, in your quiz problems, and in your exam problems, the person who authors the problem needs to give you permission to treat an interaction as if it's elastic. You need explicit permission. The problem might say, two objects collide elastically. Or it might say, they collide in such a way that the energy is conserved. The fact of the matter is, the energy is never actually conserved. But using the law of conservation of energy as an approximation gets us very, very useful results that would be impossible to get otherwise. So there's a trade-off between the approximation of assuming elasticity and the error associated when a little bit of energy escapes. Now I'd like to demonstrate the kind of problem that cannot be solved with just the assumption of the law of conservation of momentum alone. So I'm studying the law of conservation of momentum, and I'm given the following homework problem. I have two objects, A and B. A has a mass of 1 kilogram and a velocity of 2 meters per second. I look at that and I realize immediately I can calculate its momentum, and since it's traveling to the right, and I call to the right the positive direction, it has a certain amount of positive momentum. There's another object, B, that has a mass of 2 kilograms and is moving with a velocity VB of 1 meter per second, also to the right. I can calculate its momentum. So in terms of the law of conservation of momentum, everything's going okay for me. Notice also that object B's velocity is slower than object A. And so A will eventually overcome B and they will collide. What I would like to know is what will their velocities be after the collision takes place. So naturally, this sounds like a job for the law of conservation of momentum. And so I break out my practical version of the law of conservation of momentum. MAVA plus MBVB is equal to MAVA prime plus MBVB prime. What I have to do is calculate the total initial momentum, and that's easy enough. Object A has a mass of 1 kilogram and a velocity of 2 meters per second, while object B has a mass of 2 kilograms and a velocity of 1 meter per second. I did myself a favor in the choice of the problem in that the velocities are both in the positive direction, and so both the momenta are positive. On the left-hand side, I know the mass of A is 1 kilogram, but I don't know the velocity of A after a collision. That's part of the reason why I'm solving the problem. And also I know the mass of B is 2 kilograms, but I don't know the velocity of B after collision. Back to the left-hand side, it's quite easy to calculate. 1 times 2 plus 2 times 1 is 4 Newton seconds of momentum that I have on the left-hand side of the equation. On the right-hand side, I'm a little bit stuck because I don't know VA prime and I don't know VB prime. Removing the units, this equation becomes, very, very simply, 4 is equal to VA prime plus 2 VB prime. But I'm in some trouble. I do not know VA prime and I do not know VB prime. This makes this conservation of momentum problem impossible to solve. It's over. It's done. Stop. Go home. You're finished. Nothing that you can do. Unless the suggestion is made that although perfectly elastic collisions are not physically real, that this collision is very nearly perfectly elastic. This collision is described as elastic. So, as I learned in algebra class, if I have one equation with two unknowns I can't solve, what I go looking for is another equation that relates those unknowns so that I can solve those equations simultaneously. I get that equation from the law of conservation of energy. There are no potential energies in the problem, and there's no work done by non-conservative forces. If there were, then I couldn't be claiming that the energy was conserved. So the law of conservation of energy then simply states that however much kinetic energy there is to start, there must be an equal amount of kinetic energy to finish. So I write that as 1/2 ma VA squared plus 1/2 mb VB squared is equal to 1/2 ma VA prime squared plus 1/2 mb VB prime squared. Well, now I have some numbers, so just like the law of conservation of momentum, I get busy plugging them in. 1 kilogram at 2 meters per second then squared plus 2 kilograms times 1 meter per second squared. I have no trouble with plus or minus here, even if the objects were going in opposite directions, because kinetic energy is always positive. On the right side, 1 kilogram times VA prime squared plus 2 kilograms times VB prime squared. Well, on the left-hand side, this all cooks down to 1 times 4 plus 2 times 1 is 6. Now, the units on the left-hand side are joules, but it's not the total initial kinetic energy because I canceled all of the 1/2s out. That was a step that I forgot to mention. But you see, I start with my equation 1/2, 1/2, 1/2, 1/2. There's a 1/2 in every term, so I simply canceled them out when I calculated this. On the right-hand side, it's VA prime squared plus 2 VB prime squared, and I find myself with the same problem again. I do not know VA prime squared, or I don't know VA prime, and I don't know VB prime. And so this equation algebraically can't be solved. When I get the two equations together, that a solution presents itself. Here's my solution that I derived from assuming energy conservation, assuming that the collision was elastic. 6 equals VA prime squared plus 2 VB prime squared. And my conservation of momentum equation was 4 is equal to VA prime plus 2 VB prime. Now, with these two equations and two unknowns, algebra guarantees me that I can come up with a solution. I can indeed find out what VA prime is and what VB prime is. The solution is a bit tricky, though, because what I'm going to have to do is take the second equation and solve it for VA prime and then square it. Plugging that square into the first equation and then doing a little bit of algebraic massage to that, when I'll find that it's quadratic in VB prime squared, find the roots of that quadratic, reason which of those roots is the correct root, and then use that root to calculate the other velocity. That is an absolutely legitimate way to do it. You might consider trying to solve it that way just for a bit of practice. It turns out, however, if I'm a bit clever with the way I do my physics and my application of mathematical reasoning to physics, there's a much simpler way to go about this. Finding that simpler way is going to require a little bit of labor with a huge payoff at the end. I'm about to engage in a little bit of heavy algebra. So if you'd like, it's okay to simply begin following along and make sure you understand each step that I'm doing, that I'm not breaking any algebraic rules, and that the steps that I'm taking seem reasonable. Chances are you will never in your life be asked to reproduce this result. Nevertheless, I'm on my way to a very, very useful final equation, an equation that I can put in my tool belt and use to great advantage in solving problems. But it's important that I appreciate where those things come from. That's part of the nature of our scientific endeavor that we do that. So what I'm going to do is I write out my law of conservation of momentum here and my law of the conservation of, essentially, kinetic energy. And as I go, I'm going to manipulate these two equations one above the other. The momentum equation will always be on top, and the kinetic equation will always be on the bottom. The very first thing that I'm going to do is I'm going to eliminate these 1/2s in the kinetic energy equation. If I just multiply the whole thing through by 2, they go away, and they're out of my way for good. So let's imagine I've done that step. The very next thing that I'm going to do is I see that both of these equations are arranged initial to final. The total initial momentum is equal to the total final momentum. The total initial kinetic energy is equal to the total final kinetic energy. I write them that way because it's useful for problem solving. But for this demonstration, what I'd like to do is rearrange these equations so that I have everything that is A on the left-hand side and everything that is B on the right-hand side. It's simple to do. For example, in the momentum equation on top, I'm simply going to subtract mb/vb from the left-hand side to the right-hand side and subtract ma/va prime from the right-hand side to the left-hand side. I'll do the same thing for the energy equation, subtracting mb/vb squared, remember I got rid of the 1/2s, to the right-hand side and subtracting ma/va prime squared to the left-hand side. And this is what I get. MAVA minus MAVA prime on the left-hand side of my momentum equation, and my kinetic energy equation, which is starting to look a bit more like the momentum equation, MAVA squared minus MAVA prime squared on the left-hand side, and the B's on the right-hand side of both equations. I notice in my momentum equation on the top and the energy equation on the bottom, on the left-hand side I have all of the MAs, and on the right-hand side I have all of my MBs. What I'd like to do in the next step is, in the first equation, factor out MA on the left-hand side and MB on the right-hand side, and in the second equation, factor out MA on the left-hand side and MB on the right-hand side. With the masses factored out, these equations look even more similar to each other. Now, the equation for momentum, the equation on top, that equation is satisfactory just the way it is. I like it very, very much. I'm not going to manipulate it anymore. What I am going to do is make a change to the kinetic energy equation. Here I have on the left-hand side MA times the quantity VA squared minus VA prime squared. That's a difference of squares. That can be broken up into two terms, VA minus VA prime and VA plus VA prime. And the same thing can be done on the right-hand side of that equation. I can take VB prime squared minus VB squared and write it as VB prime minus VB times the quantity VB prime plus VB. Here is what that looks like. By expanding the left and the right-hand side of my energy equation, I've made things seem a little bit more messy. But I'd like you to make a fun observation with me. My momentum equation on top, which I left aside for just a moment, says that the MA times the difference of the A velocities is equal to MB times the difference of the B velocities. Now, looking below, do you see that in my energy equation, the term MA, VA minus VA prime, appears on the left-hand side, and the term MB times VB prime minus VB appears on the right-hand side? My first equation, my momentum equation, says that those two are equal to each other, and so I can cancel it from the left-hand side and the right-hand side because those two terms are equal to each other. That leaves me with simply VA plus VA prime on the left-hand side and VB prime plus VB on the right-hand side. Now I'm very nearly at my final result. What I have is VA plus VA prime is equal to VB prime plus VB. I have all the A's on the left-hand side and all the b's on the right-hand side. And that's perfectly fine, except that I know from my problem solving and thinking about my physics that I'd much prefer to have everything initial on the left-hand side and everything final on the right-hand side. Well, that's easy to do. All I have to do is subtract VB from the right side to the left side and subtract VA prime from the left-hand side to the right-hand side. And what I'm left with is my final result, the equation that I was looking for. VA minus VB is equal to VB prime minus VA prime. This equation has no squares in it. And so when I'm trying to solve elastic collision problems, this equation makes it much, much easier to do the algebra. I have to stress there that this equation can only be used to solve elastic collisions. The reason why is that my algebra all the way up to this point started from the assumption that the energy was conserved in the collision. In collisions where the energy is not conserved, for example, collisions where things collide and stick together, this equation is not valid and cannot be used. So you really can only use it when the problem you're trying to solve explicitly states that the collision is elastic, or that during the collision the energy is conserved. I have just such a problem that I've been working on, that collision between object A and B that I applied the conservation of momentum to but couldn't solve. I can now apply this new equation that I derived for myself. Recall I had these two objects, A and B. A, 1 kilogram moving with 2 meters per second, and B, 2 kilograms moving at 1 meter per second. And I applied the law of conservation of momentum, and I got this vexing equation that I couldn't solve. 4 is equal to VA prime plus 2 VB prime. I have one equation, but I need another equation in order to solve. That equation that I'm going to use is my new elastic collision equation. I can only use this because I made the claim that the collision between these two objects is in fact elastic. So all I have to do is plug these numbers in and I'll get a second equation that I can leverage algebraically to get me the answers. What is VA prime and what is VB prime? The velocities of A and B after the collision. So along with my conservation of momentum equation, I now also have my elastic equation, where it's the velocity of A, which is 2 meters per second, minus the velocity of B, 1 meter per second, appears on the left-hand side. On the right-hand side, I still don't know what VB prime is, and I still don't know what VA prime is. My strategy for solving the problem will be to solve the second equation for VA prime and plug that into the first equation where VA prime appears. By doing that, I'll then have one equation that has only VB prime in it. Solving the second equation for VA prime leads me to VA prime is equal to VB prime minus 1. And so I'll take that VA prime and insert it into the first equation. 4 is equal to VA prime plus 2 VB prime. And that gives me one equation explicitly in terms of VB prime that I can solve, because now 4 is equal to VB prime minus 1 plus 2 VB prime. A VB prime plus 2 VB primes is 3 VB primes minus 1, adding 1 to the left-hand side. Then 5 is equal to 3 VB prime, and I found VB prime, the velocity of B after collision. It's 5/3 of a meter per second, an answer I could not have gotten from the conservation of momentum alone. I needed help from the conservation of energy. Once I have VB prime, VA prime is an easy get, because I already know that VA prime is equal to VB prime minus 1. So VA prime is 5/3 of a meter per second. Minus 1 meter per second is 2/3 of a meter per second. And so I've arrived at my two results. VA prime is equal to 2/3 of a meter per second, and VB prime is equal to 5/3 of a meter per second. Results that I could not have obtained without assuming that the collision was elastic. These results, by the way, they make an awful lot of sense. A was originally traveling at 2 meters per second. When it hits B from behind, A will feel a force opposite its direction of motion, and so I expect it to slow. And indeed it has, going from 2 meters per second to 2/3 of a meter per second. B is hit from behind. Traveling at 1 meter per second, it experiences a force in its direction of motion. So then I expect it to be going faster after the collision, and indeed it is, at 5/3 of a meter per second. So the law of conservation of energy and the law of conservation of momentum are working together in many different interactions, and it can help me solve problems. I have to appreciate the fact that this is an approximation. It can only be done under specific circumstances, and the results have a certain amount of error associated with them in the calculations. However, it makes it possible for me to investigate areas of my universe that were formerly inaccessible.